Good morning students, welcome back to session 3 of vector spaces classes. So this is a continuation part of session 2. So as I said, linear dependency or independency of the vectors does not depend on only the vector space but as well as the field. So because if we take the vector space C over R, set of complex over reals and set of complex over complexes. Okay, in this we can see that 1 comma I belongs to C. 1 comma I are elements of C, but 1 comma I is linearly independent in C over R. C are linearly independent over C over R, but they are linearly dependent on C over C. C over C. Okay. So next we are going to prove an important theorem. Say it states, suppose Vf is any vector space and V1, V2, etc. Vn are in V, then they are linearly independent. Then they are linearly independent, or some vector say Vk is a linear combination of preceding ones. Vk is a linear combination of preceding ones. Preceding ones means V1, V2, etc. Vk minus 1 means in a vector space the vectors are linearly independent, or some vector is a linear combination of preceding ones. Okay, means they are dependent. Linear combination of preceding ones means what? One is dependent on the other. Yes, you take the proof. Suppose if V1, V2, etc. Vn are linearly independent, then there is nothing to prove. Okay, so let they are linearly dependent. So you assume that they are linearly dependent. If linearly dependent means there exist scalars C1, C2, etc. Cn in F, such that the linear combination C1 V1 plus C2 V2, etc. Cn Vn is equal to 0. So now I will assume that let k be the largest index for which Ck is not equal to 0. Let k be the largest index such that Ck is equal to 0. So such choice is always possible because at the most k may be equal to n. Maximum k may be equal to n. Now Ck is the largest index for which k is not equal to 0 means what? Ck plus 1, Ck plus 2, etc. up to Cn, they are all zeros. Okay, then the above relation becomes C1 V1 plus C2 V2, etc. Cn Vn is equal to 0. This implies what will happen? Ck Vk is equal to minus C1 V1 minus C2 V2, etc. minus Ck minus 1 Vk minus 1. So this implies now Ck is not equal to 0 and it is an element of F, means Ck inverse exists because every non-zero element has inverse in a field. So Vk is equal to, so I will multiply throughout by Ck inverse. So this becomes minus Ck inverse into C1 into V1 plus minus Ck inverse into C2 into V2 and so on. The last term is minus Ck inverse into Ck minus 1 into Vk minus 1. Thus, we have seen that Vk is a linear combination because this I can write it as d1 V1 plus d2 V2, etc. dk minus 1 Vk minus 1. What is di? Di is nothing but minus Ck inverse into Ci. So definitely this is also an element of F. Okay, so Vk can be written as linear combination of preceding vectors. Okay, now let us look at the other important definition, that is basis of a vector space. Basis of a vector space. Suppose we have a subset S of the vector space Vf, then we say S is a basis for V if S spans V. First condition is S spans V, that is L of S is equal to V. L of S is equal to V, and S is linearly independent. If the set S spans V as well as S is linearly independent, then we say S forms a basis of V. Again, I'll take up the previous example where V is R2 over R and the set S is 1 0 0 1 1 0 0 1. So you know that S spans V. Already we have shown it. L of S is equal to, the condition means L of S is equal to V here. So, and also we have shown that this set is linearly independent. Okay, S is linearly, second condition is S is linearly independent. Therefore, S forms a basis of R2 or basis of V. Likewise, I can take any vector space and a corresponding basis. Okay. Say for example, you take R3 over R. The vector space V over F is R3 over R. So then you find which are the bases for R3 over R. Okay, R3 over R. Next, say we have a theorem. Say suppose we have a set S which contains elements V1, V2, etc. Vn. Suppose this is a basis of V. Suppose this is a basis of V. Then you know that every element of V can be uniquely expressed as a linear combination of elements of S. If S forms a basis of V, then every element of V can be uniquely expressible as a linear combination of elements of V. We know that if S forms a basis, then every element is a linear combination of V1, V2, etc. Vn, because S spans V. So now that linear combination is unique, we need to prove. Okay. Suppose the element V be written like alpha 1 V1, etc. alpha n Vn, alpha is belongs to F, and the same element V being also written as say beta 1 V1 and so on, beta n Vn, where each beta I belongs to F. Okay. So then V is equal to V means, so alpha 1 V1 plus alpha 2 V2, etc. alpha n Vn is equal to beta 1 V1, beta 2 V2 and so on, beta n Vn. So this implies what? Alpha 1 minus beta 1 times V1 plus alpha 2 minus beta 2 times V2 and so on, alpha n minus beta n Vn is equal to 0. But V1, V2, etc. Vn are linearly independent, means each alpha is must be, alpha I minus beta I must be 0. Each alpha I minus beta I is equal to 0. For every I takes the value from 1 to etc. n. This means what? Alpha I is equal to beta I, means, so if you return V as a linear combination of this and this, then alpha I must be equal to beta I, means every element of V can be uniquely expressed, okay, uniquely expressed as an element of S. Now we are going to prove one important theorem. That theorem says, every finite dimensional vector space as a basis. Every finite dimensional, I will write finite dimensional vector space FDVS. This is the only abbreviation. So finite dimensional vector space as a basis. Every finite dimensional vector space as a basis. Okay. In fact, every vector space as a basis. Okay. Every vector space as a basis. So proof. Suppose V is a finite dimensional vector space. V is a finite dimensional vector space. Then by definition of a finite dimensional vector space, V is generated by some finite set. So S is a finite set here. Okay. S contains say V1, V2, etc. Vn. So V is generated by the finite set. Okay. Now if S is linearly independent, then what will, sorry, S is linearly independent, then S itself forms a basis of V. S itself forms a basis of V. If not, suppose S is not linearly independent, then what will happen? So by definition, by already learned result, so if S is not linearly independent, then some vector Vk is a linear combination of preceding ones. Say Vk is equal to, say, beta 1 V1 plus beta 2 V2, etc. beta k minus 1 Vk minus 1. This is a linear combination of preceding ones. Now you take the set S1 V, which is S minus Vk. You delete this element, which is a linear combination of preceding ones. So this is what? V1, V2, etc. Vk minus 1. Vk is not there, so this is Vk plus 1 and so on, Vk, Vn. Then definitely S1 contains in S properly. S1 is contained in S. This implies what? L of S1 is contained in L of S. This already you know this result. You call this as, say, by number 1. Okay. Now V belongs to L of S. Now V belongs to S, L of S implies what? V can be written as alpha 1 V1, etc. alpha k minus 1 Vk minus 1 plus alpha k Vk. Here alpha k is, Vk is an element of S. Okay, so this is equal to alpha n Vn, alpha n Vn. So this is equal to alpha 1 V1 and so on, alpha k minus 1 Vk minus 1 plus alpha k into, in place of Vk I write, since Vk is a linear combination of preceding ones, I write the value of Vk here. So alpha k into beta 1 V1 and so on, beta k minus 1 Vk minus 1. Next, as usual, say this is alpha k plus 1 Vk plus 1 and so on, alpha k, sorry, alpha n Vn. So this is equal to, so now alpha 1 V1 is also here and alpha k beta times V1 is also here. So you combine those. So alpha 1 plus alpha k into beta 1 into V1 and so on up to k minus 1 terms. Alpha k minus 1 plus alpha k into beta k minus 1 into Vk minus 1. The next element as usual, alpha k plus 1 into Vk plus 1 and so on, alpha n Vn. So definitely these are all scalars that lies in F only. Therefore we can see that V is a linear combination of elements of S1. So here Vk is not there. Therefore this belongs to where? L of S1. Now we have taken the element in L of S and we have shown that the element belongs to L of S1. Therefore what you can say? L of S is contained in L of S1. So we call this as number 2. Already we have shown L of S1 is contained in L of S and now we have shown L of S is contained in L of S1. Therefore linear span of S is same as linear span of S1. Linear span of S is same as linear span of S1. Now if S1 is linearly independent, then S1 forms a basis. If S1 is linearly independent, then S1 forms a basis. S1 forms a basis. Okay, S1 forms a basis and the proof will be finished. Otherwise you continue the argument. So next you delete some element which is a linear combination of preceding ones in S1. Okay, so you make it S2 and so on. Finally we will have definitely some Sk with at least one element. At least one, definitely Sk has at least one element because that set has to span V. Okay, Sk is S minus V1, V2, etc. Vk definitely has at least one element and V is equal to L of Sk and Sk is linearly independent. Therefore every vector space has a basis. Okay, so I proved it for the finite case. In fact every vector space has a basis. Now let us take up another important lemma. or small result. Say suppose v1, v2, etc. vn is a basis for v. Suppose v1, v2, etc. vn is a basis for v. And if w1, w2, the elements wm are linearly independent in v. Suppose the vectors w1, w2, etc. wm are linearly independent in v, then this number of vectors is definitely less than or equal to number of basis elements. The number of linearly independent vectors is always less than or equal to the number of basis elements. Okay. So for this, so I'll take the set S1 which contains wm, v1, v2, etc. vn. I'll consider the set S1 as wm. I added wm to this set vn. Now wm belongs to v and v1, v2, etc. these are the bases. v1, v2, etc. vn is a basis, implies wm can be written as linear combination, say alpha 1 v1, alpha 2 v2, etc. alpha n vn. Alpha n vn. Also clearly S1 spans v. Means from this, the spanning set contains more elements. Okay. And since wm can be written as a linear combination of the preceding ones, wm can be written as a linear combination of preceding ones, S1 is linearly dependent. Although it spans v, it is linearly dependent. Okay. So linearly dependent means some say since S1 spans v, some proper subset of S1 definitely forms a basis of v. Say that proper subset, say I may choose wm. So some vector I will delete from this combination. Say I will rename the new set of vectors as wm, vi1, vi2, etc. vik, where k is how much? Maximum, the value of k is, I remove the one vector, so the maximum value of k is n minus 1, because total n vectors must be there here only. Okay. So we have this process called the trading off process. Trading off process means we have traded off the element wm and we have given this one. One of the elements in v1, v2, etc. vn we have given by taking one of the element in this one w's, wi's. Okay. So now repeat the above procedure. So you repeat the above procedure with the set say you take wm minus 1, you replace another vector, say wm already there, you take another vector wm minus 1. If you take wm minus 1, definitely some vector has to be deleted from this set of vectors. Say this I will this you may call it as vj1, vj2, etc. vj say r and vjr, where r is what? R is less than or equal to say r is less than or equal to what? Yeah, this is n minus 2. R is less than or equal to n minus 2 because we have taken maximum value for r is n minus 2 only, because we replace two elements. Similarly, I can replace say wm and wm minus 1, etc. up to wr I will replace. So this becomes v say s1, vs2, etc. vs again I will write it as k, vsk, where k takes the value which is less than or equal to n minus how many elements we have replaced. So this is say up to, this is not wr, w2. How many elements we have replaced? M minus 1 elements were replaced. Okay. So wm minus 1 up to w2, w1 not taken, so we write the other remaining elements. Remaining elements means what, the value of k must be less than or equal to m minus 1 we have element replaced. Okay. So now since the set W1, W2, etc. Wm is linearly independent, linearly independent, so W1 we cannot write as a linear combination of preceding ones. So there exists at least one Vji. So if I include Wi1 also here, then W1 cannot be written as a linear combination of preceding. Suppose we ended up here itself. Suppose we ended up here. What will happen if we if we ended up here, then W1 will become a linear combination of preceding ones, but it is not true. So at least one of the elements remains here. In other words, saying that, say we removed all the elements Wm minus 1, etc., W2, W1, okay, and so that this is a set, new set, which spans V, and also which is linearly independent, therefore it forms a basis. Then that case, what will happen? W1 becomes a linear combination of preceding ones. So it cannot be. So at least there exists at least one Vji, to write W1 as a linear combination. Means at least one element should be there, means what? R must be, or K must be this one. R must be greater than or equal to 1. R must be greater than or equal to 1 implies what? Sorry, this is K must be greater than or equal to 1. K must be greater than or equal to 1 means what? N minus K is what? Maximum N minus M minus 1, N minus M minus 1 must be greater than or equal to 1. If N minus M minus 1 must be greater than or equal to 1 means what? This implies N minus 1. This implies N minus 1 is greater than or equal to M minus 1. N minus 1 is greater than or equal to M minus 1 means N is greater than or equal to M. N is greater than or equal to M, or M is less than or equal to 1 means the number of linearly independent vectors are always less than or equal to the number of basis elements. So it has one small corollary for this result. That corollary says, so if we have two sets of basis elements, the corollary says, if there are two sets of basis elements, for any vector space V, say we have, suppose S1 is one basis containing V1, V2, etc., Vn, and S2 is another basis containing W1, W2, etc., Wm, then M must be equal to 1. Means the number of basis elements in any vector space must be the same. Okay. So let us prove this by the above result. Suppose S1 is basis. S2 is linearly independent set. Then by the above result, what will happen? S1 is a basis and S2 is linearly independent means N must be greater than or equal to M. Is it true? The number of basis elements must be greater than or equal to number of linearly independent vectors. N must be greater than or equal to M. Next we consider S2 is a basis. And S1 is linearly independent. Now S2 is a basis and S1 is linearly independent means again M must be greater than or equal to N. Therefore M must be equal to N. Means the number of basis elements in any vector space is the same. For example, in R2 over R the vector space, you can see that S1 is equal to 1 0 0 1 forms a basis. We can see that S2 containing 1 1 1 0 also forms a basis. Also forms a basis of R2 over R. But the number of elements in S1 and S2 must be the same. Likewise, you can take any vector space and a basis, the number of basis elements must be the same. Okay. So from the above discussion, we can also see that, so although the number of elements in the spanning set may be more than the number of basis elements, okay, the spanning set of any vector space V may contain more number of elements than the basis number of elements. It may contain more number of elements, but it cannot contain lesser than elements. Okay, we cannot span the vector space which is less than the number of basis elements. Okay, that will be compulsory. And note that also if S is linearly independent, say containing say a number of vectors Vn, S is the basis for the vector space V, means linearly independent. Suppose if you consider S dash which is contains lesser number of elements than the set S, then that set may be linearly independent, because subset of a linearly independent set is linearly independent, but that cannot form a basis. Okay, so linearly independent set may contain lesser number of elements, that also linearly independent, but it cannot form a basis. And the linear spanning set may contain more number of elements, that set will not become linearly independent, it becomes a linearly dependent set. Therefore, for a basis, okay, the number of linearly independent vectors must be, say if we have the S is the set having n number of basis elements, then the spanning set also must contain, any spanning set must also contain n number of elements, and that elements must be linearly independent only. Okay, that's all for this class. Thank you.